Hello everyone, this is Xiao from Duke University. Today I'm going to present our work on aggregated deletion propagation for counting conjunctive query answers. This is a joint work with Shouzhuo, Shweta, Debmalya, and Sudeepa. View update has been studied for a long time in the database literature, which investigates how to change the database to obtain desired changes to the query output. It enables users to tune the query answers in order to meet their prior expectation, such as by external constraints or compare multiple options. In this paper, we study a natural class of view update problem as aggregated deletion propagation, and the target is to remove at least a given number of query results by removing tuples from the database. There are two motivations for the ADP problem. First, it can be used to obtain a desired change in the output size with minimal intervention on the inputs. This example is for managing waiting list for the class in a university. Bob is on the waiting list for a database class. If Bob intends to major in CS and CS requires a database course, and there are no seats available in the database course, the university may try to figure out the easiest alternative for reducing the size of a waiting list to some target, which corresponds to removing tuples from the input database. Secondly, ADP can be used to analyze the robustness of the output with respect to the possible disruption in the input. In a communication network, if it were possible to disrupt about 80% of the path by only removing 1% of the link, then the network is clearly not robust. On the other hand, if this would require removing about 80% of the links, this is a much more robust network. This is precisely the information that the ADP can provide us on this query. Now, let me give a formal definition of the ADP problem. We study the class of conjunctive query, where the body is a set of relations joining on their common attributes, and the head is a subset of attributes appearing in the body, denoted as output attributes. The ADP problem takes three parameters as inputs: a conjunctive query Q, a database D, and the parameter key. As mentioned before, the target is to find a minimum subset of input tuples from D, such that removing them can remove at least the key query results of Q over D. In this example, removing either tuple A2, B2 from R1 or C3, E3 from R3 can remove two query results. So the solution of ADP QD2 follows this observation. We studied the complexity of this problem. We can see the query has constant size and use the number of tuples in the database as complexity measurement. And in this paper, we want to answer this question. For which class of conjunctive queries, the ADP problem is polytom solvable? We give an algorithm that can take the query as input and efficiently decides whether ADP can be solved in polytom on Q for all instances and all values of key. To complement our algorithmic characterization, we also provide a structure characterization by identifying three simple structures whose presence exactly captures all queries while the ADP is NPhard. Due to the time limit, I will only show the algorithmic dichotomy in today's talk, and more interesting details on the structural dichotomy can be found in our full paper. In addition, we give a practical unified algorithm for solving ADP for all conjunctive queries, which returns the optimal solution for easy queries and the polytom heuristic for hard queries. Let's start with two base cases. If there's no output attribute, such a conjunctive query is Boolean, which indicates whether the joint result of the input relations is empty or not. The ADP problem on the Boolean query is also known as the resilience problem, which has been well studied in a VLDB paper in 2015. If there exists one vacuum relation whose attributes are empty, the ADP problem is always easy. The essence of this decision procedure is two simplification steps: removing an attribute that appears in all relations and decomposing a disconnected query. Both steps preserve the hardness of the ADP problem. Consider an example query. As defined, A is a universal attribute. So the polytime solvability of Q is equivalent to the residual query by removing A from all relations. Then we get a disconnected query, and the polytime solvability of Q is equivalent to the logical end of every connected subquery. Putting everything together, we come to a complete description of this decision procedure. The high-level idea is to alternately apply two simplification steps on the input query until a base case is reached. We first remove all universal attributes. If Q becomes Boolean or contains a vacuum relation, it is decidable in polytime. Next, we check whether it is connected or not. For this connected query, we decompose into multiple connected subqueries and call this procedure recursively on each one. Otherwise, Q ends up in the others category, and this procedure always returns false. Continue with the previous example. We first remove attribute A and decompose the residual query into two connected subqueries. We further apply the simplifications on the first subquery and end up with two easy base cases. However, the second subquery falls into the others category, so it is hard. By combining the results of all subqueries, we conclude that ADP problem on the original query is NPhard. It's worth mentioning that the hardness of ADP problem comes from bipartite graph. For example, this query is exactly captured by the partial vertex cover problem, which finds the smallest number of vertices such that at least key edges can be covered. And how to prove their hardness and how to map general queries to this hard course can be found in our full paper. Our practical algorithm follows the same framework as the decision procedure with two dynamic programming and one heuristic. Let me give some high-level idea. Assume attribute A is a universal attribute. We can divide the input tuples into groups by their values on A. The query results are also divided by attribute A. Then we reduce the original problem into a set of subproblems on the residual query, one group of input tuples and a parameter ki. The only constraint is that the sum of the query results removed by all groups is at least k. The target is to minimize the sum of input tuples removed from each group. When Q is disconnected, define the lambda I as the output size Qi. Note that the original query is the Cartesian product of all subqueries. In this way, we can reduce the original problem into a set of subproblems on each subquery, the original database, and the parameter ki. Similarly, the constraint is to remove at least the ku query results while minimizing the sum of input tuples removed. When no more simplification steps can be applied, we invoke the greedy heuristics. It chooses a tuple with the largest profit iteratively, which is defined as the number of query results that can be removed by removing this single tuple. This strategy achieves log k approximation for some class of queries, but no theoretical guarantees for general queries. A more drastic strategy is to remove tuples only from one relation. This is much more efficient as the profit of tuples in one relation are independently defined, and one iteration of computing the profits is sufficient. But there is no theoretical guarantees for this drastic version. As shown in this experiment, drastic greedy is much more efficient than greedy, and on this TPCH dataset, they find solutions for the ADP with the same quality. Finally, I would like to conclude this talk by mentioning several open questions. First, it would be interesting to study the ADP problem beyond conjunctive queries, in particular when functional dependency, self-joins, or aggregates exist. It's also natural to consider scenarios where all input tuples are not equivalent in terms of the cost of removing them. For example, only a subset of input tuples can be removed. Secondly, further investigating the approximability of the ADP problem is another interesting research direction, which is unclear even for the special case of resilience problem. A related question is an FPT algorithm for the ADP with respect to the parameter k. Thank you for your listening.